Welcome back to The Explainer. Today, we're diving into a genuinely fascinating, high-stakes topic in distributed systems, database replication. We are going to look at exactly how modern applications manage to keep our data alive and kicking through almost any hardware failure or network outage you can imagine.
To really wrap our heads around the scale of what we're talking about here, I want you to picture Netflix. Right now, at this exact moment, Netflix is serving roughly 200 million users simultaneously. You've got people all over the planet logging in, saving their watch progress, tweaking their profiles every single second. That is a massive, relentless flood of data just hammering their backend.
So here's the million-dollar question. What happens if the specific database server handling your profile completely crashes, right at this very second? Well, the answer is absolutely nothing. You'd keep right on watching your show without a single hiccup. Why? Because your data doesn't live on just one server. It lives on many. By the end of this explainer, you're going to understand the exact mechanics of how systems like Netflix, Amazon, and Google actually pull this magic off behind the scenes.
Let's start with part 1. Why database replication exists. Basically, it just means keeping a copy of the exact same data on multiple different machines.
Engineers are usually chasing three massive benefits here. Think of replication like keeping copies of a super important paper document in multiple locked safes across different cities. First up, we get high availability. If the safe in New York gets jammed, no problem. We just fly to the one in Chicago. In system terms, if one server fails, another takes over instantly and the user has no idea anything even went wrong. Second is durability. Now, this is a concept we covered extensively back in episode 2, right? If the building with the New York safe actually burns to the ground, the document still exists somewhere else. Your data is safe. And third, we get read scaling. If 100 people need to read that document at the exact same time, having multiple copies means they don't all have to stand in a massive line at just one safe. We distribute those read queries across all the replicas, which massively reduces the load on any single machine.
Moving on to Section 2, Single Leader Models and the choice between synchronous and asynchronous. This is by far the most common architecture you'll see in the wild.
The easiest way to understand single leader replication is to think of a major national newspaper. There is only one editorial team. That's our leader server. All the new articles, all the writes, go strictly to them. Once they write the news, they record it in a ledger and send the final copy out to printing presses in different cities, and those are our follower servers. The followers just blindly apply the exact same changes in the exact same order and print the papers. Readers can buy the paper from any local press, meaning they can read from any follower, but they absolutely cannot submit new articles to that local press. Only the central leader accepts writes. And hey, for those of you who caught episode 1, this should sound incredibly familiar. That ledger the leader uses to record changes before sending them out, that is built on the exact same write-ahead log, or wall, foundation we talked about. The wall is literally the replication log. It's all connected.
But here is where engineers have to make a really tough choice about how the leader talks to the followers. We have synchronous versus asynchronous replication. Synchronous replication is kind of like sending a highly sensitive email and forcing the recipient to send you a read receipt before you do anything else. It is incredibly safe. You know for a fact the follower has the data. But it's slow. Your application is entirely blocked, just sitting there waiting for that network round trip. Asynchronous replication, on the other hand, is like leaving a voicemail and immediately hanging up. It's incredibly fast because you aren't waiting around for a response. The application moves on instantly. But it carries a pretty big risk, right? You don't actually know if they'll ever listen to that voicemail before, say, dropping their phone in a lake. If the leader crashes before the followers catch up, any of those recent writes are just lost forever.
If this is the kind of content you want more of, subscribing takes 1 second and it genuinely helps the channel grow.
Okay, Section 3, Replication Lag Consistency Problems. Because, as it turns out, that asynchronous voicemail approach comes with a bit of a dark side.
See, because followers are always catching up, they are always slightly behind the leader. It's exactly like news spreading through a city entirely by word of mouth. Let's say the mayor announces a new law. That's our right to the leader. Some downtown neighborhoods hear about it instantly, but the suburbs, they might not know for another 10 minutes. This lag causes our first major issue, the read your own rights violation. Imagine this relatable scenario. You post a comment on a post. That right goes directly to the leader server. Success. Then you immediately hit refresh on your browser. But this time, your read request is routed to a follower server to balance the load. Because of replication lag, that specific follower hasn't received your comment from the leader yet. You look at the screen and your comment has just vanished. You panic. You think it was deleted, so you submit it again.
It's a terrible user experience, and it's caused entirely by back-end replication lag.
Beyond your own writes vanishing, there are two other famous anomalies you should know about. First is the monotonic read violation, which is basically time travel. You refresh your page and hit an up-to-date follower, so you see a brand new comment. Cool. You refresh again a second later, but this time you hit a slow, lagging follower. The comment disappears. The data appears to literally go backward in time. Then there's the causality violation. This one is trippy. It happens when a reply to a comment reaches a follower before the original comment does. So to the user reading from that follower, they see a reply to a ghost message that doesn't even exist yet.
Section 4. Multi-leader and conflict resolution. To solve some of these global-scale issues, some systems move away from having just one single leader.
Think of a multi-leader setup like two editors working on the exact same offline Google Doc from different countries. Because they're both leaders, they can both accept writes immediately without waiting for the other. It's super fast. But what happens when those two offline Google Docs finally reconnect to the internet? Well, the system has to merge them. And if both editors change the exact same sentence, boom, we have a write conflict. The system has to decide who wins. The easiest method is last write wins, which literally just looks at the timestamp and keeps the newest edit, though this totally risks silently deleting the older edit. Alternatively, you can merge the values, which works great for things like a like counter, where you just add the numbers together. Or you can push it to the application level. That means you force the software's custom code or even the user to manually resolve the conflict, exactly like Git does when you get a merge conflict.
All right, Section 5. Leaderless replication and quorum. What if we just get rid of leaders entirely? Systems like Cassandra and Amazon DynamoDB do exactly this.
Instead of a single editor in charge, think of this like a jury system. To reach a verdict, you don't need everyone to be perfectly in sync at all times. You just need a majority, a quorum. Even if one juror is asleep or absent, as long as the majority agrees, the whole system works. Engineers use a simple piece of conversational math for this called the quorum formula. W plus R must be strictly greater than N. Let's break that down. It's actually really simple. N is the total number of replicas you have. Let's say we have 3 servers in total, so N is 3. W is how many servers must confirm a write, and R is how many servers you must query for a read. If we set W to 2, it means every time we save data, we force at least 2 out of the 3 servers to confirm they saved it. If we set R to 2, it means every time we read data, we ask 2 different servers what they have. Because 2 plus 2 equals 4, which is strictly greater than our 3 total servers, the math guarantees that our read request will definitively overlap with at least one server that saw our latest write. We will always get the freshest data, and we did it without needing a leader.
Finally, Section 6. The CAP Theorem trade-offs. All of these different models exist because of one unavoidable absolute rule in distributed systems. CAP stands for consistency, availability, and partition tolerance. The CAP theorem states that you literally cannot have all 3 of these properties perfectly at the same time when things go wrong. And because network cables get cut, routers crash, and servers lose power, network failures, known as partitions, the P in CAP, are completely unavoidable. You absolutely have to tolerate partitions. So, during a network partition, real systems are forced to make a brutal, hard choice between consistency and availability. Do you choose consistency, meaning you actively refuse to answer a user's query just to prevent them from seeing stale, lagging data? Or do you choose availability, meaning you always answer the user's request to keep the app feeling fast and responsive, even if you know the data they are looking at might be slightly outdated? Every single database architecture we've discussed today leans one way or the other on this specific trade-off. To wrap this all up, let's quickly recap our journey. We started with single leader, where only one node accepts writes. That gives us 0 conflict risk, but makes us vulnerable if that one leader goes down. This is your classic Postgres or MySQL setup. Then we looked at multi-leader, allowing multiple nodes to take writes. That is amazing for global speed, but introduces high conflict risk, often used in complex multi-region setups. Finally, we explored leaderless, where any node takes writes and we rely on that quorum math to find the truth. That gives us medium conflict risk, but incredible resilience, like you'd see in Cassandra or DynamoDB. Replication completely solves the problem of keeping data safe and available by making copies, but I'm going to leave you with this final provocative thought. What happens when your application becomes so unbelievably massive, I'm talking billions and billions of rows of data, that an entire copy of your database simply cannot physically fit onto a single server's hard drive anymore? How on earth do you replicate something that is literally too big to be copied as a whole? Well, that is the fascinating problem of sharding, and it's exactly where we'll be picking up next time. Thanks for exploring this with me today.